Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. Today we're going to be talking about the quotient rule, which is another important rule for differentiation with important consequences for integration. And we're going to start moving towards this knotty problem of dealing with division in the world of polynomials or polynumbers. So that's often the most challenging arithmetical operation, and dealing with it forces us to rethink a lot of very foundational issues, and that's going to have really important consequences for the direction of the algebraic calculus. Okay, so the starting point is, first of all, just a notion of division when one polynumber p divides another polynumber q. So that happens precisely when q equals r times p for some polynumber r. And then here's the quotient rule, which tells us that if p divides q, then the derivative of the quotient q divided by p has this expression: p dq minus q dp over p squared. This is a little bit different from the way it's often presented, so that I want you to think about it this way. So the p here is in the denominator and the q is in the numerator. We're assuming that p does divide q, so this is actually a polynumber inside here. And this formula is telling us how to find the derivative of that polynumber purely in terms of the numerator and the denominator. And the expression p dq minus q dp, of course, should resonate with you because that's a fundamental ingredient of the fundamental theorem of the algebraic calculus. Now, note that in particular, since the left-hand side is a polynumber, because it's the derivative of a polynumber, so the right-hand side must also be a polynumber, which means that p squared has to divide this cumulative numerator p dq minus q dp. That's a consequence of the validity of this formula. So a simple example: if q equals 1 minus alpha cubed and p equals 1 minus alpha, then indeed p does divide q. And the quotient rule tells us that the derivative of the quotient will be p dq, there's p, there's the derivative of q, minus q dp, all divided by p squared. Well, the numerator here simplifies to 1 minus 3 alpha squared plus 2 alpha cubed. And that actually has a factorization: 1 minus 2 alpha plus alpha squared times 1 plus 2 alpha. And that term is the same as 1 minus alpha squared. And we do end up getting 1 plus 2 alpha, which is the derivative of the quotient, because q divided by p is 1 plus alpha squared. So in this case, doing the division is not hard, and we could then just differentiate the result of that division directly, but the rule allows us to do that without actually performing the division first. Now I want you to note that we're assuming that p divides q, that we are not writing the expression this way. So this is an alternate form that is sometimes found in texts, but I want to steer away from this alternate form. The alternate form is when you take the two ingredients in the numerator and separate them. So d of q over p equals 1 over p dq minus q times dp over p squared. The reason why this doesn't work is because it's actually not defined, because we're just working in the realm of polynumbers here. And this expression by itself, the derivative of q divided by p, is not necessarily a polynumber. In other words, that's a division that does not necessarily work. Similarly, this division does not necessarily work. What works is when you combine the p dq minus q dp, then that combination is divisible by p squared. Okay, so we don't want to make the mistake of using this alternate form. So I just point that out. Okay, but here is an alternate form that's quite useful. So suppose that we write q equals r times p. So r is q over p. Then the derivative of this q over p, same as the derivative of r, can be rewritten as P dq, we just replace the q with Rp, minus Q dp, we replace the q with Rp, all over p squared. So now there are no more q's in this expression. We've rewritten it purely in terms of r and p. And then there's a common factor of p here, so we can cancel those. We get d of Rp minus r dp all over p. And this then is an alternate form of the quotient rule, and we see now why the quotient rule is satisfied, because this thing here is just essentially equivalent to the usual product rule that the derivative of Rp equals r dp plus p dr. Right? What we've got here is just a rewriting of this, where we've taken this and we've subtracted this, and then we've divided by p. Right, so that's like a proof of the quotient rule from the product rule. Now I want to give a little application of the quotient rule in a somewhat novel direction to something I call an integral transmutation theorem. Transmutation referring to changing something from one form to a different form. What we're doing is we're taking an integral of one kind and changing it to get an integral of a seemingly different kind. This is the kind of thing that Leibniz was interested in, and so we're sort of following his footsteps here. This is the formula that I want to show you. That p and r are two arbitrary polynumbers, and the rule is that 2 times the signed area from t to u of p pr equals the signed y area from t to u of p squared r. So we have two different curves here. The first curve is the curve formed with p and pr. Those are the first and second coordinates. And the second curve has components p squared and r. For the first one, we're looking at a traditional signed area, subtended from the origin as usual. And the other half, we're dealing with a signed y area. It's like the area to the left of the curve, or better perhaps the area between the curve and the y-axis. And there's a factor of 2 here. Okay, so why is it true? Well, let's consider q, which is r times p. Then, from the quotient rule, p squared dr equals p dq minus q dp. This is just a rewriting of that form that I showed you before. And now we're going to integrate this with the Faulhaber integral S, capital S. So the Faulhaber integral S from t to u of p squared dr is going to be equal to the Faulhaber integral from t to u of p dq minus q dp. But we recognize this is just a fundamental theorem kind of expression. This is just 2 times the signed area from t to u of pq. That's what the fundamental theorem says. The fundamental theorem says that this signed area is 1/2 of this Faulhaber integral. And on the left-hand side, we recognize that this is of the form of a signed y integral. Okay, because there's something times d of something else. So this is the signed y integral from t to u of p squared r. And so we get the expression here, and then we can replace the q with pr, and we get the original term here. All right, so let me give you an example of this transmutation theorem in action. Let's choose p to be polynumber 1 plus alpha, and r to be simply alpha. Then, on one side, we have 2 times the signed integral, let's say from 0 to 1 to keep things simple, of p pr. All right, so p is 1 plus alpha, and p times r will be alpha plus alpha squared. So we're talking about 2 times the signed area of this curve, 1 plus alpha, alpha plus alpha squared. Well, this is a quadratic curve. It's a parabola, And here is the portion of the parabola that's relevant. Here, 1 plus alpha, alpha plus alpha squared. It's there. It's not a line, it's part of a parabola, but just that portion that we're interested in. When alpha is 0, we're at the point 1, 0. And when alpha is 1, we're at the point 2, 2 up here. Okay, so that's the curve we're interested in, and we're talking about the signed area from 0 to 1. So that's this, the usual signed area from here to here, subtended by the curve, and then we multiply by 2. And it's an easy calculation that is 7/3. Now what about this thing here? The other side is the signed y area from 0 to 1 of p squared comma r. So that's the signed y area from 0 to 1 of 1 plus alpha squared comma alpha. Well, that's another quadratic curve, and it looks like this. It's part of a parabola going like this. There it is there. When alpha is equal to 0, we're at the point 1, 0, same as before. And when alpha is equal to 1, we're at the point 2 squared, which is 4, comma 1, which is up here. So there's that curve there. And we're talking about the signed y area of this curve. So that's the area bounded by the curve and the y-axis. It's this green area here. That's the signed y area of this curve here. So the claim is that this red area here, if we multiply that by 2, then we get the green area there. And these are different kinds of integrals. First of all, the curves are different. And the first one is a signed area, in the classical sense, subtended by the origin, while the second one is a signed y area between the curve and the y-axis. So we're somehow able to go from one of these to the other by this simple transmutation. So whenever we can transform an integral in some way to rewrite it to give us quite a different form of it, well, that's good, because then it gives us a handle on some situations. We might be able to transform or transmute a particular example to something which is more amenable to calculation. Now let's have a look at a slightly more complicated example of the quotient rule. Let's observe that 1 minus alpha plus alpha squared happens to divide 1 minus alpha to the 6. So we're able to ask about the derivative of this quotient, 1 minus alpha to the 6 divided by 1 minus alpha plus alpha squared. And the quotient rule tells us that it's this bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. And then you work that all out, and it turns out to be the polynumber 1 minus 3 alpha squared minus 4 alpha cubed. Now, actually sort of involved here, to understand this division here, 1 minus alpha to the 6 actually has a decomposition in terms of irreducible factors. It's actually the product of 1 minus alpha times 1 plus alpha times 1 minus alpha plus alpha squared times 1 plus alpha squared. And this is kind of a special case of quite an important family of polynumbers, the 1 minus alpha to the n, that we'll have more to say about that at some later point in the courses. But anyway, this thing here shows you that indeed 1 minus alpha plus alpha squared does indeed divide this, so justifying this. And we can also see what the quotient is directly. The quotient directly is just the product of these two, 1 minus alpha squared, times this term here, 1 plus alpha squared, and you can multiply that out to get 1 plus alpha minus alpha cubed minus alpha to the 4th. And so then we can check that everything is all right, because if we take the derivative of this, we're going to get 0, 1 minus 3 alpha squared, and minus 4 alpha cubed, as the quotient rule tells us. So we see here that we're touching base, though, with the divisibility of polynumbers, the factorizability of polynumbers, and basically it's arithmetic with polynumbers, but in the direction of division. And unfortunately, division is very subtle. It's the most difficult operation of the four classical ones. and, well, brings some challenges for us. So we're going to have a look at division. So these days, I'm not sure if students really learn long division anymore in primary school. They ought to, but chances are they don't, which is very unfortunate, and it's particularly problematic when they get to algebra and calculus, because long division plays a very big, important role in calculus, as we'll see. So let's give an example of how I want you to perhaps think about long division for polynumbers. Okay, we're first of all working in polyret, which for me is the polynumbers with rational coefficients. Most of the examples I will give you actually have integer coefficients, but technically rational coefficients are allowed. We want to work in that more general framework. And I want to illustrate how we could, say, divide 1 minus alpha to the 6th by 1 minus alpha plus alpha squared, the same example that we had in the previous slide, without actually performing that factorization or knowing that factorization. So we can do this directly by long division. And it's a simpler long division than that with numbers. Okay, this is a simpler long division. So that's good. And I'm also setting it up in a particular way. So I want you to do something like what I'm suggesting here. So we have to figure out how many times this polynumber divides into 1 minus alpha to the 6th. By the way, the Math Foundation 64 video talks a little bit more about this if you want to have some more information. Okay, so what we do is we write 1 minus alpha to the 6th divided by 1 minus alpha plus alpha squared. We write a bar, and we'll make a little vertical line here, and we're going to do some work over here, and our answer is going to be output here, all right? So what we're going to do is we're going to start by asking how many times will this thing here fit into here if we're only concerned with this first sort of top entry, the 1. How many of these can we fit into here? So what number should we put here so that this times this actually equals this? The answer is 1. Okay. So one of these is 1 minus alpha plus alpha squared. So we're going to take this and we're going to subtract this. We're going to subtract 1 times this. Okay, so what do we get? 1 minus 1 is 0. There's no alphas up here, so when we subtract this, we'll get a single alpha. We'll get a minus alpha squared and a minus alpha to the 6th. Okay, now we ask the same question, how many of these fit into this thing? And again, all what we do is we look at the first entry here, which is 1, and the first entry here, which is alpha. It's particularly simple. We see that we have to multiply this by alpha in order to get an alpha that matches the one that's here. So we multiply by alpha, and we write down the product of this thing with alpha, which is right there. And we perform the subtraction. Alpha minus alpha is 0. Minus alpha squared minus alpha squared, it's 0. And then we have to also subtract alpha cubed, and there will also be a minus alpha to the 6th. Okay, there we are currently. We ask how many times does this thing fit into here? Well, we just look at this first term, minus alpha cubed. So we put minus alpha cubed because then this number times that will give us exactly a minus alpha cubed there. We'll also get alpha to the 4th and minus alpha to the 5th. And then when we do the subtraction, we get minus alpha to the 4th plus alpha to the 5th minus alpha to the 6th. Okay, I haven't finished yet, so there's at least one more thing to do. So now we do it again. We ask how many of these things fit inside here. The answer will be minus alpha to the 4th. So we'll write down minus alpha to the 4th times this. Minus alpha to the 4th plus alpha to the 5th minus alpha to the 6th. And then we do the subtraction, and happily we get 0. Okay, so we now are finished the process. We've divided this thing by this thing an exact number of times. We've gotten a remainder of 0, and this is then the quotient. Okay, so that's how we do long division for polynumbers. Okay, I have to say a few words now about the difficulties with division, even for primary school mathematics, because it turns out that the difficulties that occur there have direct ramifications and direct correspondences with difficulties in the calculus. And in fact, the direction of the calculus from where we are now depends a lot in understanding certain issues having to do with division. Okay, so to get you in the spirit here, let's think about just division of numbers. Let's say somebody asks you, what is 24 divided by 6? Well, you will know that the answer is 4. And how do you know that? You know it because you've memorized a multiplication table beforehand. And in that multiplication table, you know that 4 times 6 is 24. So if somebody asks you 24 divided by 6, you recall the multiplication table and you can remember that the other factor is 4. Now suppose that I ask you, what is 24 divided by 5? Well, the multiplication table now no longer helps you because the multiples of 5 don't include 24. But we have an extended number system now, okay? So we have this decimal number system that extends our arithmetic from integers to these more general things, decimal numbers. And with this extended arithmetic, we can answer this question of what 24 divided by 5 is. It's 4.8. This is the Hindu-Arabic decimal system, but really the idea goes back to the ancient Babylonians who did exactly this kind of thing, but in their base 60 or sexagesimal system. Notably though, what's important here is that we're dividing by 5, which happens to be a factor of our base. Or more generally, it's composed of factors from our base. Our base is 10, it has factors 2 and 5. So dividing by numbers which are built from 2s and 5s is a lot simpler than dividing by other numbers in our decimal system. Because exactly those divisions that result in finite decimal answers. The Babylonians knew this very well. In their base 60 system, it's actually richer because they can divide by 3 as well as 2 and 5. So the numbers that they can divide exactly by far exceed the ones that we can divide exactly by. So there's actually a more powerful arithmetic when it comes to this all-important operation of division. But what if we divide, say, by 7? What is 24 divided by 7? Well, that's a very interesting question, okay? So the old Babylonians would have said, and they do say in their tablets, 24 divided by 7. 7 does not divide. This is just not an operation that has an exact answer in the Babylonian system. Now, we have several alternate, more elaborate number systems that are designed to exactly solve this problem. Okay, so we're going beyond integer arithmetic, beyond decimal number arithmetic. There are now these two new arithmetical frameworks that students learn about, exactly so that they can proceed with this kind of non-regular division. Okay, and these two frameworks are fractions and repeating decimals. So with fractions, what we do is we say, okay, what's 24 divided by 7? The answer is it's the fraction 24 over 7. Now, Babylonian would have looked a little bit askew at this. So, some sleight of hand here. You're not actually dividing, you're just sort of promising to divide. You haven't divided yet. And there's some truth to that, right? We're just writing this thing down. Maybe later on, if we're doing some algebra, that 7 in the denominator there will cancel with a 7 in the numerator somewhere else. And we'll avoid ever having the problem of having to divide by that 7. So there is a bit of sleight of hand involved with this fraction system. But nevertheless, very powerful theoretical framework for doing arithmetic in a way that incorporates division fully. At least if you remember not to divide by 0. So this is a theoretically easy framework. Well, not easy for primary students, but it is possible to lay out what's going on with fractions very concretely and explicitly, prove all the laws of arithmetic, and it's a very nice exercise. But practically, this is a very hard system. If you're actually doing calculations in the real world and you're working with fractions, they will overwhelm you very quickly because even if you're adding fractions, the denominators multiply. And so the numbers that you're getting are bigger and bigger. The numerators and the denominators get overwhelming. So you end up with these big fractions, and it's hard to look at them and easily say just how big these numbers are. So practically speaking, this is actually not a very manageable system for ordinary life. And that's why in ordinary life, we use this other system, well, preferably this one, the Babylonian system, of decimals. Because with decimals, you can tell very easily how big a number is just by looking at the leftmost digits. Okay, but to deal with 24/7, then, there is this other system, which is an extension of the decimal system, which we might call the repeating decimal system. Okay, with repeating decimals, you kind of perform the long division, much as I've shown you, and you get something like 3.428571. And then if you keep on doing it, you notice that it repeats. And so you end up with this repeating decimal, where the bar over here means that the 428,571 keeps on repeating. Now this is practically pretty easy because it's very close to the decimal system, and we can convert from here to here very quickly just by truncating. If we're only interested in a certain amount of accuracy, we just truncate at a certain point, and then we're back in this system here, which we understand very well. However, theoretically, this is actually a very hard system. Okay? The actual theoretical foundations for arithmetic with repeating decimals has, I think it's fair to say, nowhere been written down properly. It's like a major folklore in modern mathematics that, somewhere somebody has worked this out. But if you want to actually write algorithms that will add or subtract or multiply or divide with repeating decimals, it's very onerous. And then to prove that those algorithms actually satisfy the laws of arithmetic that you would like, I claim this has not been done. It hasn't been done. So theoretically, this is actually hugely challenging. And of course, it's just one step to the even more challenging system of so-called real numbers, where we consider infinite decimals that don't necessarily have any repeating pattern. Okay, that's even more bizarrely uncomputable and without foundation from my point of view. But nevertheless, I'm not saying that you couldn't do this. It's actually quite an interesting challenge. So this is not impossible to set up such a theory. It's just that in my view, nobody has done it. Okay? But nevertheless, these two examples will pave the way for our thinking with polynumbers. So they're crucial kind of alternatives when we're setting up calculus, because we want to go one step up from numbers to polynumbers. And then both of these paths lead to very rich mathematics, but we have to navigate those paths very carefully. All right, so how are we going to extend the algebraic calculus from polynumbers to allow division? This is a very big question and a challenge for us. It's going to open up all kinds of new areas. So let me just give you a rough orientation to the two main avenues of tackling this question. We're going to introduce ultimately things called quotient polynumbers and then things called recurrent polynumbers. And this is just a brief indication of something in this direction. So suppose we're interested in 1 plus alpha cubed divided by 1 plus 2 alpha. Now, this polynumber does not divide this one, so we cannot get a resulting quotient polynumber. Nevertheless, what we can do is we can do the same kind of thing as we did with fractions. We can introduce a formal object where we write down an expression with this thing here in the numerator and this thing here in the denominator, and we call this a quotient polynumber. And then the result of this division is this quotient polynumber. And happily, the theoretical foundations for quotient polynumbers is really just the same as for fractions almost. It's very parallel. And so we can set up such an arithmetical system. And then to answer the question, in this context, it turns out that the Faulhaber derivative operation, capital D, extends very pleasantly from polynumbers to these quotient polynumbers. How? Just by using the quotient rule. The quotient rule tells us exactly how we should take the derivative of such a thing. And the result is another quotient polynumber. And then we can check, there's quite a lot of work to be done, but we can check that pretty well all of the understandings and formulas and sort of theory that we've developed for the derivative for polynumbers extends to this wider, more broader framework. But, and it's a big but, the situation is very different when we come to the integration question. Extending the Faulhaber integral operator S to quotient polynumbers is much more problematic. In fact, it only extends partially. Only extends partially. So understanding this and its ramifications is going to be something that occupies us a lot. And we're going to have to be much more careful about this than classical calculus courses. Classical calculus courses cheat in a huge way when it comes to this topic. It's almost all wrong what they're saying, really, to be honest with you. Okay, so we're going to have to do things in a much more careful and more precise way. And you will see that that opens up all kinds of new understandings for us. A lot of this is going to be happening in Algebraic Calculus Two. Okay, and in that course also we're going to be looking at this other side of the same question, where we introduce things called recurrent polynumbers. So same question, 1 plus alpha cubed divided by 1 plus 2 alpha. Here's another possible answer to what is this quotient. We can introduce something which is a polynumber equivalent to a repeating decimal, but it's more complicated. So we're not going to say repeating polynumber, we'll say recurrent polynumber. In this case here, what we end up, and notice there's quotes here, so this is just an informal indication of what's going on. This is not a precise statement. We're getting something that looks like 1 minus 2 alpha plus 4 alpha squared minus 7 alpha cubed plus 14 alpha to the 4th minus 28 alpha to the 5th plus 56 alpha to the 6th minus, and then there's these 3 dots. And you'd be forgiven for not being very confident about what those 3 dots mean. Okay. There seems to be some pattern here. It's sort of like doubling by 2, except from this stage here. We're not doubling by 2 there, but otherwise it seems that we're doubling by 2. So does it continue like this? Do we just keep on doubling by 2? Or at some point do we make a jump, just like we've done here? So that's not clear at all. Nevertheless, there is a way of working with these kinds of things, identifying what they are, and then we're in a position to ask the same kinds of questions. Can the derivative operator be extended to these new kinds of recurrent polynumbers? And if so, how does that work? Do we get a consistent theory? And can the integration operator also be extended? So something like this happens, okay, that the derivative operator is a lot more amenable to exact analysis. We'll be able to say exactly what happens with the derivative operator, but with the integral operator, it is much more complicated, okay? But the complication has a different form. So we're going to be touching base with a lot of new mathematics based on this challenge, this need to extend our algebraic calculus from polynumbers to more general objects, which incorporates division. And the quotient rule is playing a very important role in this. So some of these ideas are going to be developed at length in the Algebraic Calculus Two course. Okay, but I just want to flag them now. I want to put them on the table. These are going to be important things for us. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.